Our topic focuses on security and privacy of searchable encrypted cloud data. This report has 5 parts: dynamic searchable encryption and thread, Oblivious RAM and its program. 3. Our solution, OBI, a key set Oblivious RAM. 4. Single path ORAMs and multi-path ORAMs. 5. Experiments and future directions. Our new techniques are multi-path ORAM and 2 eviction algorithms. Let us make a short introduction to dynamic searchable encryption. DSE is a user called protocol for efficient searchable encrypted cloud data. This protocol involves 2 parties, the user and the cloud. We assume the user is trusted and the cloud is curious but honest. To search over the encrypted data, the user first needs to upload an encrypted index generated by encrypting a set of data files. In the second stage, the user invokes the DSE protocol to search a keyword. For example, the user searches football and fetches a set of file identifier results set. In the third stage, the user updates directly the encrypted database by using an encrypted token. For example, the user wants to insert a keyword by into the second file. Most traditional DSE protocols mix search patterns and access patterns in data searching and data updating. The SAP attack proposed in Usenet security showed that the keyword football and bag can be recovered by the hackers with some probability, only if the background knowledge is pure. It is well known that using Oblivious RAM is a good choice to thwart SAP. In CCS 2018, the DSE scheme ORAM is proposed. ORAM makes back both use of an Oblivious map. It is an Oblivious data structure built on PATH-ORAM. We found that ORAM and the ORAM-based DSE scheme suffer from a new problem. It is inefficient to process a large result set. We call this problem the large eviction problem. In short, it is stated as follows: how to evict a large data block stored in the stash obviously and efficiently. That is, when we obviously insert or delete a large result set, we should re-encrypt and evict the stash blocks stored in the stash. Assuming the stash stores all data blocks and R is large, a straightforward idea is to repeatedly invoke PATH-ORAM to insert values. However, this process requires ORAMs and or spread time. For example, assume the stash has 2 R blocks. PATH-ORAM can insert 1 data block per query in the average pace. For each insertion, PATH-ORAM should scan the whole stash to choose a valid block for insertion. It takes big O R time per query. Thus, the whole insertion time is about big O R squared complexity. Another straightforward idea is to insert all the data blocks into the ORAM tree in one batch. We can add an additional loop to the original PATH-ORAM eviction algorithm. However, this algorithm still consumes big O R squared time per query. It still suffers from the large stash eviction problem. To address LSEP, we proposed a new DSE scheme named OBI. OBI is not OBI is a key set Oblivious RAM. The key set Oblivious RAM is not a key value Oblivious RAM. So a key set Oblivious RAM can be generated from a key value array. To distinguish these two concepts, we list the difference in this table. First, the key set array in general has size pattern leakage, but the key value array leaks nothing. Secondly, the key set array is high throughput, but the key value array is low throughput. Thirdly, the position map of the key set array can be small compared with the key value array. Finally, the key set array is a multipath array if it has a multipath eviction algorithm. Therefore, we should deeply study the key set array. OB is an obvious inverted index. It is also a key set array. We embed an inverted index into the ORAM tree. The data structure of OB has three parts: the ORAM tree, OT, the hash table, HT, and the slash set, and the slash ST. OT is for data storage. HT acts as the position map of PATH-ORAM, and ST is the local slash set. HT differs from PATH-ORAM simply use a pseudo-random function to compute the positions of data blocks. This helps us save storage space. Compared with PATH-ORAM, a data block has three parts: key, value, leaf. GW concatenated 1 is the key field. 52 is the value field. 8 is the leaf identifier field. A data block can be stored in the tree or in the slash. In this graph, G is a pseudo-random function. GW concatenated 1 is the first keyword identifier. This is the second keyword identifier. Since these two keyword identifiers exist in different paths, we read all the paths containing the keyword identifier in one time. After data reading, we re-encrypt and evict the data blocks stored in the stash into the original paths in one time. Our experiment showed that we can insert all the stash blocks into the paths with large probability, assuming some conditions are satisfied. We use two new eviction algorithms to address the large slash eviction problem, KNEA and PBEA. Since the eviction algorithm is relatively complex, in this report, we do not want to introduce the eviction algorithm in details. We assume you are familiar with PATH-ORAM. The KNEA algorithm is a multipath eviction algorithm. It evicts the stash blocks into the multipaths in one batch. This graph shows the working process of KNEA. To fill a tree node with some stash triplets, stash blocks, instead of scanning the core stash, we find only the cleanest labels of the data blocks whose leaf identifier are near to the current path. For example, to insert into node file, the algorithm inserted into node file scans only K data block in the stash. However, KNEA should maintain a sorted array. In KNEA, removing the inserted block from the sorted stash takes big O R time, below the insertion. Thus, the insertion time is big O R squared. This table shows the eviction time complexity of KNEA and and PATH-ORAM. When the stash is small, the eviction time is the main part. KNEA is similar to PATH-ORAM. When the stash is large, the eviction time is the main part. KNEA saves two multiplicative factors, log n and T0. T0 is the time to test a valid block insertion. It's near log n. The second is the non-recursive PATH-ORAM. The third is the non-recursive multipath ORAM, which is a multipath ORAM. We add an additional loop to the original algorithm. Can outperform PATH-ORAM when the stash is large. However, can either do not address NDSS completely. We should use PBEA to further address the NDSS. We propose PBEA to further address the large stash eviction problem. PBEA is a partition-based eviction algorithm. We partition the stash and the open tree into R sub-partitions and a root partition. Next, we evict the partitioned slash block into the partitioned subtrees. Partitioned blocks into the partitioned subtrees. While this is work well, note that the data block can be evicted into only one corresponding partition. We cannot evict the block into other partition according to the eviction rules. For each sub-partition, we invoke KNMEA to process the sub-partition eviction. It can be concluded that PBEA works in big O R log n time to process the whole slash. PBEA is far more efficient than PATH-ORAM. We classify the Oblivious RAMs into single-path ORAMs and multipath ORAMs. A multipath ORAM is an ORAM that has a multipath eviction algorithm. A single-path ORAM is an ORAM where any query reads only one path. While we define the multipath ORAM, from the aforementioned conclusion, we can see that multipath ORAMs have some advantages to process a large result set. The following ORAMs are single-path ORAMs. The non-recursive PATH-ORAM and the recursive PATH-ORAM are single-path ORAMs. ODS in CCS is a single-path ORAM. Ring ORAM in useless security is a single-path ORAM. Only ring ORAM is a single-path ORAM. HIRB in SNP is a single-path ORAM. They all are single-path ORAMs. Is it a single-path ORAM? URAS are. URAS, it is a single-path ORAM. URAS is a DSE scheme proposed by New 30 EDL in TDSC. URAS is a single-path ORAM. Since URAS need a single path per query. PATH-ORAM is also a single-path ORAM. PATH-ORAM is also a single-path ORAM. PATH-ORAM is an oblivious single-path PATH-ORAM, so it has multiple clients. So this PATH-ORAM is an oblivious single-path PATH-ORAM. We proved that the multipath ORAM outperforms the single-path ORAM in terms of stash size and insertion efficiency. From our paper, we conclude the following inequality. The probability of stash size exceeding big R is less than a fixed value. Where big R is a positive value, small r is the number of reading paths per query. Here R equals 4, and alpha 1, alpha 2 are constants. This inequality shows that we can increase R to improve insertion efficiency. We can use OBI to set up a multipath or Oblivious file system. We propose a prototype of multipath Oblivious file system. Our key idea is to save all the directory names on the local disk and save all the data files into the open tree. Assuming each data file has the same size, to obliviously and read the full directory. We read all the paths. PBEA to write the data box into the own tree. We use queries to add the reading paths to the fixed set. In the experiment, we proved that OB outperforms PATH-ORAM in a slash on the slash side when the slash is given, when the large S is given. Our setting now, we use a single thread marked as eviction algorithm. The data block has 32 file identifier. Our results, when inserting 1 million class, PATH-ORAM requires 3 lower, KNE requires 11 minutes, PBE takes only 40 seconds. This is because PATH-ORAM suffers from the large slash eviction problem. In this experiment, we proved that OB outperforms ORAM on bandwidth. Our setting, big R is the result size. Big R equals 1024. Z is the bucket size. L is the head of the tree. There are 3 reasons. OB uses a locally stored position map, but ORAM uses a recursive position map. ORAM is not optimized for locality. 3. ORAM is a single path ORAM. It suffers from the large slash eviction problem. This time, this graph shows the running time of OB. ORAM takes 400 million milliseconds to fetch 1024 results. OB takes only 10 milliseconds to fetch 1024 results. We summarize our contributions as follows. First, we proved that the multi-path ORAM outperforms the single-path ORAM in terms of slash size and insertion efficiency. Second, we proposed a key set mapping multi-path ORAM. 3. We give 2 new eviction algorithms, KNE and PBE. 4. We propose ZPHOBI, the first efficient set-path-having DSE scheme. We gave an obvious persistent prototype. We also give an obvious conjunctive-query scheme, OCQ. This graph shows some hot topics of dynamic searchable encryption in recent years. As for future directions, some notations should be further studied. 1. Oblivious multipath key-value PATH-ORAM. Second, Oblivious multipath key-set PATH-ORAM. Third, multipath multi-user Oblivious RAM. Okay, thank you, the chairman and Frank. Thank you for listening. Sorry, my spoken English is not good. If you have any question, send a mail or message to me. Thank you. That's all.